Hello everyone, and thank you. I reintroduce myself as part of the introduction of this presentation. So I run a project named OpenGeoStat. I started that when there was a big slowdown in the mining industry, so I had a little bit of extra time to start coding and saving money on software. And as a main product of this, well, I got something called PyGeoSleep, which is GeoSleep for trunk code connected to Python and extra tools I use for resource estimation. You can actually do a resource estimation with that. And it works very similar to data mine. You write a script, and you basically do everything from loading data to interpolating a model and creating some geological interpretation. So I do all this work related to resource estimation, and at some point started experimenting with machine learning, using machine learning for resource estimation. As part of this work as well, I present training, and I promote machine learning as a tool for all geologists. So don't expect to see very advanced technology here. My point here is that it's another tool, and we can all use it in a quick and efficient way. And this is what I'm trying to present today. So machine learning, there is no official definition for that, but for me it's basically a toolbox. That can be classified in techniques for supervised learning, unsupervised learning, and other techniques that you take and adjust to your needs, like time series segmentation. We will see an example of that. And you can use to do regression, to interpolate a variable, or to classify rocks, things like that. But the point is just a toolbox. You have to pick the technique you need for each specific case. Well, the tools I use, since I come from a very Pythonic way of working, I have picked Orange from Biolab. This is an open source software. The big advantage of that, you can run on your computer. You don't have to upload your client's data to the cloud or anything like that. And it's very well documented, and many people are using this. And it's very simple to use. So it goes the graphic user interface. You just drag things and connect it properly, and you get the results. You decide if the results are good or not. I also work with Sklearn, which is also open source, and for more advanced work, I work with a combination of TensorFlow and Keras, and Sklearn as well. But Orange is simple enough, and it comes with a bunch of tools for machine learning. And it got extensions as well. So you can do things like sentiment analysis to analyze how well you're doing in these talks, or how people say about you in Twitter, things like that. It's actually one of the examples we have in one of our training courses, so using this kind of data. But today, I will be focused on the use of machine learning for resource estimation. Personally, I solve problems with machine learning with supervised classification. I do a lot of automatic Drillhole logging, logging cleaning. So we get our interpretation from the geologists in the field, and sometimes it's too messy. You have to clean it up before you can build a model. And machine learning is a good way to speed up the process with a good quality output. To do regression, for example, to interpolate or decide what density you will assign based on chemical data. Time series segmentation is an example I will expand later, and other tools like exploratory data analysis and unsupervised classification, which I'm not very a fan of it, because unsupervised classification tends to change a lot. Just by changing tiny parameters, it's hard to track if it's working or not. But I will show examples at the end, if we have time. So time to show some examples. And we'll start with Drillhole logging using machine learning. So the problem one, we have a data set which is really messy. We have a lot of lithology code, and we want to try to homogenize that and simplify it a little bit and remove outliers to build our geological model. So the solution for this is modifying the classical Drillhole logging system to remove the outliers. And I will show you how I do it. So this is the classical workflow for Drillhole logging system using machine learning. You start with data. You do a little bit of pre-processing. You test your data. You generate a model, and then you export this model and reuse it with new data coming from the field. You can integrate that to a data management system and do automatic classification in different type of rocks, but starting from a training data set. Okay? That's very easy to implement in Orange, actually. So this is how it looks in Orange. You just basically take your training data. That's okay. That's this tiny sphere we got over here. You do some pre-processing, and then basically you feed with data to a test and score with something that pick data, train it, and then calculate the error or misclassification of different techniques. And then you measure how well you're performing. You analyze your data, and you pick the best technique. You export the model. And this is a production stage where you import new Drillhole data. You have already your model predefined. You classify it, and then you get the output. The modified machine learning workflow, it's slightly different. So you basically, how I go back? Okay. So you basically train the data set, you feed the model, you remove all the outliers, and then retrain the data set, and then you iterate until you get a cleaner model that is way more simple and easy to use for resource estimation. So this is how it looks in an implementation in Orange. So you start with the model, you train it. Here you select all the properly classified data and remove the outliers, and feed the data, the output, to a new training set, and remove more outlier, and you keep going until you get a level of error that you accept. Once you're happy, you take this model, you save it, and then you retrain all your data. It's very simple. So you basically retrain all the bad log samples, and you assign a new logging. And with that, then you start the resource estimation part, reinterpreting the model and doing all the work. Okay? The interpretation, it's very visual, so you can see where the outliers are, the meaning, the correlation with different geochemical variables, and doing like a geological meaning of the error, and decide if the model is performing well or not. And you can quantify the probability to be in one lithology class or the other. So this is how it looks in Excel once you train the model. You export your data to Excel, and you see that you have different lithology types. This is using geological data from Flim Flow, but this is a toy example, but it shows very clearly how it works with real data. I do that kind of analysis quite often in my consulting work, and it gives you the probability associated to each lithology. So it's not like lithology A or B, it's the probability to be in lithology A. Sometimes you have a second candidate, and you can interpret it. You can do that with your chemical data, of course, and do the analysis of all the errors. This is another interesting tool, or the interesting example. This is the long log description from a Drillhole dataset. So you can take this textual data and do a kind of filtering and pre-processing to convert the words in a numerical quantities that can be processed with any standard machine learning technique. Well, there are few that works okay with this type of data. This is an example how it is implemented in Orange. So you just basically import your Drillhole data, pre-process, you clean it, pre-process, and then you use a machine learning technique to do classification, and this is the output. So you get the probability to each lithology only using this long description. So that may work if your geologists are kind of consistent. But if you have, for example, 3 generations of logging, or you have geologists logging the data that comes and back, or a senior geologist who's trying to keep homogeneous the way it's described, it may work in many cases. Okay? Problem 2. So in this case, this is a real example, consulting work. I won't mention the name of the client. But we had a data set, a large data set we've used to do a resource estimation. But the density and the lithologies associated to each density class were sampled in a very limited amount of points using spatial density measurement technique or data collection technique. So the trick here is that we have to put that information in the block model. So the solution was taking the geochemical data from the block to decide what lithology, density lithology group it's each block, and then assign the density. The other restriction is that this is an operating mind, so the model is evolving all the time. So you don't want to give them a very complicated model that you have to use Python to reuse that. So I decided to go with a very simple technique, which is not the best of all, but when it works well, it's easy to interpret. It's called classification tree or decision tree, and it can be visualized in Orange with the tree viewer. So this is the output. This is automatically generated, and the amazing thing is that it reproduces exactly the kind of lithology classification they use on site, but that techniques finds first the variable who better splits the two groups using information theory measures, and then it creates this kind of trees that you can switch, extend. So if you click here, you extend or reduce the tree. So you can early stop the tree based on the number of pairs. And it gives you a good also threshold where to cut or split two groups of lithology. The other interesting output of this example is that we have lithology 1, 2, 3, 4. My feeling was that lithology 1 and 2 were very close, and it's probably a good idea to merge it, and that's one of the output I got in this example. Most of lithology 2 are merged into lithology 1, and sometimes it jumped to lithology 3, so I let the algorithm ignore lithology 2 and place those blocks in one or the other. The advantage of this technique is that you can read it as a human and implement it in Excel, or just write a script to select with if and then options what class is your block, which class is your block. Okay, it's very easy to do. Other techniques are way more complicated than that, so you cannot. It's just basically a Python script declassified, and you cannot read that. The problem 3, and this is another confidential example. So we have a data set with 48,000 drill holes. And I have to come out with a wireframe and interpolate in this block model. So the geology in this case is similar to a stratigraphic sequence, not exactly that. And the solution was using time series segmentation to split intervals in the drill holes automatically and ignore repetition of lithologies. But let me show you an example how it looks. So this is how the original logging looks like. So if you are working in leapfrog, you have to manually say, well, this is lithology 1, then you have lithology 2 in between, and then what happened? What I do in that case? I cut here, I put the sample up and down. You can do that manually with 48,000 drill hole and with multiple intervals per drill hole. So the idea was using time series segmentation to reinterpret and trying to join all the intervals to a very simple and continuous sequence. The next part is just taking the contact point and using a radial basin function, interpolate surface, and that's it. You got your model. Of course, there is a quality control in between. So you have metrics to find errors. You do a validation, but it's easier doing a validation in 48,000 drill hole data set than doing all the work manually. Okay. So this is how it works. It basically takes splits and minimize the less square sum of all the possible split in the drill holes. It's very good algorithms to do like grade shells as well. So decide which group range of values split better the two lithologies. And if I have more example in case I had extra time to talk. So I'm quickly going to show you. This example is from, that one is not an easy one. So this is the kind of work that when you face difficult examples, the other you can do it really quickly. For this one, you need more time to set up the thing. And here is using convolutional neural network to do automatic image interpretation for a televiewer image. This is data from TriStar Gold, and the project is in Brazil. So it works. It identify pebbles in a paleoplacer gold deposits very well. So these red things are the probability to have pebbles. And so you can do modeling, place your wireframe here, and this is your interpolation area. Unfortunately, it's a difficult problem because you have so many variation in the image that sometimes you misclassify like fractures as pebbles, but you can improve the algorithms doing extra work. I didn't continue working on this example. And something I am doing some kind of advocacy are techniques based on one class classifier. So that's a way around. So you can come out with a method that it only focuses in the thing you are looking for, and you don't care about other things like cracks or things like that. And this method has a lot of potential to use machine learning for exploration and targeting. For example, I'm looking for a epithermal deposit, and you don't care what is the lithology you got around, and you just want to calculate the probability to be an epithermal deposit. One example of this class are the autoencoders. There are more than that. One class support vector machine, other techniques that can be used. And finally, a quick example. This one was the output of a training course. I had clients. I'm a resource geologist, but my clients were exploration geologists, and they were doing a lot of non-supervised classification. But the problem with non-supervised, you change something and all the classification change. So it's very unstable. We had to come out with a way to quantify how good is the classification, and this is a good example implemented in Orange that tells you how well is the classification. So that's a measure of error for a non-supervised classification technique. In conclusion, machine learning can be easy and productive to use. The first set of example, we're talking about a few minutes to set up everything and come out with results. So it's very productive. But you may wisely select the appropriate technique for each case. So that's a human component here. And you may also identify how to learn, how to identify difficult problems that require more work before you jump into to solve the problem. My recommendation is down low and play a little bit with Orange. And if you want a more formal training, we have a training course on machine learning using Orange as well, which have been presented in the past in-house for some clients.